Welcome back. This is the last lecture. Finally, we made it. You have to survive for 45 minutes. So before starting, I just want to make a historical correction. It's been a long time. I was thinking I should modify this slide that I have in my lecture, but I always keep forgetting to do it, and so now I'll do it. So what I called sour lemma yesterday is actually not due to sour in the first place, but to Plastic and Charbonnenkis, who proved it the first. Then I think sour proved it again, but without knowing the proof of Plastic and Charbonnenkis, and then Chelar also did its proof independently of this sort of proof. That's just, I think it's important to have the right names. Okay, so in this lecture, I want to diverge a bit from what I was saying before. So this is not in the lecture notes. And that's a bit philosophical in some sense. I want to somehow give you an overview and some general comments on why is it good to do learning theory and what is interesting in learning theory and what are the risks of doing learning theory. I will tell you about two notions, error bound, and see, maybe try to give you a more detailed idea of what that is. And then we see what is a good bound, because we've been talking about bounds and we don't really know what they are used for somehow. We have just seen the techniques, but not really the practical implications. And then I will a bit discuss about what is the best approach. Is it MDL, Gaussian processes, kernel methods? We have seen a lot of different approaches, and everybody was comparing these results with the others. And this, every time you see that you do better with RVM than with SVM, or you do better than with GP than with SVM in some cases. So, who should we trust? And of course, this is personal view. So, you are allowed to disagree with me, and please do so even loud. So, across the slide, I have put this sign, this red box, and this means that I'm making somewhat strong claims, but I don't have the formal proof for it, and it reflects my own personal opinion, and of course you may disagree.
Otherwise, you cannot.
Yeah, the rest is maybe taken as mathematical truths. Okay, so we talked a lot about the empirical error, and well, you probably know, and I'm sure you know, that there are also ways to estimate the error. And I have listed some ways here. So just to write them, and well, maybe a picture is better than long explanation. So you have some data. There are several ways you can test your algorithm. One is you train on the whole data and you compute the error that you make on this whole data. So that's the empirical error. Now the second approach is to predict it in two parts. So this is what's called the holdout set that you keep on the side. You train only on this part and you test your algorithm on this part. You compute the error on these validation sets. Okay, and the nice thing is that this is independent from this, so you don't introduce extra bias in your estimates. And you can do this in a slightly different way, cross-validation. So you do this repeatedly by taking chunks in your data sets, training on all the chunks except one, and testing on the one that you have left, and so on. You remove this chunk, train on the other, test on this one, and so on. You take an average, that's a cross-validation error, and you can do this in an extreme way where the chunk is actually reduced to one example. You leave out one example, that's why it's called leave one out, and you train on the rest and test on this one. And this gives you another estimate of the error. So all these estimates have advantages and inconveniences, and basically you can quantify their difference in terms of bias and variance. For example, if you look at the empirical error, since we train on the same data that we test on, of course we will have a small error, because that's what we're trying to do. We're trying to minimize the error on this training sample. So it will be biased towards low values, which may not reflect the actual true error. So there is a large bias in this estimator, but on the other hand, we gain that we have a nice control on the variance of this estimator via this error bound that we discussed before. So that's what means favorably biased means biased towards low error. And at the extreme, I mean at the other end of the spectrum, you have the leave one out error, which is it's called almost unbiased, because when you take the expected value of this leave one out error for sampling sample set of size n, then it gives you the expected error of your algorithm when it's used on samples of size n minus 1, because you always take one guy out. Okay, so it's an equality here. So on average, the leave one out error is a very good estimator because it's almost unbiased. But the problem is that it's very hard to control the variance, and there is no general statement that you can make on that variance. There are except in very specific cases, there are no bounds on the leave one out error. So then it's a matter of choice, whether you want to use an estimator which is unbiased, but of which you don't control anything, or if you want to use a biased estimator, but for which you have clear bounds. Okay, so that's what it says here. Which one should I prefer? Depends mostly on what you want to do. The bounds we have for the empirical error, for example, they give us guarantees. So we know we have some kind of mathematical statement that tells us the error cannot exceed this quantity with a very high probability that we can quantify precisely. Okay? But on the other hand, when we do that, when we are using our algorithm and we need to estimate the error for tuning certain parameter, for example, well, okay, it's good to have guarantees, but it may be better to have something that is actually close to the behavior of the algorithm. And leave one out error in general, in practice, closer to the true error. So in practice, it may be better to use these other bounds, other quantity estimates. But on the other hand, bounds tell you something, because these estimates of the error, the leave one out error, you can compute it fine, but you cannot really say that you understand something once you compute this estimate. Whereas with the empirical error, when you do this analysis that leads you to being bounds, I mean, a large set of new quantities appear along the way. For example, the BC dimension, I mean, came out from this analysis in some sense. So, and the fact that the margin plays a role in the SVM and is related to the capacity, that's also something that comes out of this analysis. So, if you really, I mean, if your goal is to use an estimate in practice, then maybe it's better to use cross validation or leave one out. But if your goal is to understand something about your algorithm, then maybe it's better to use the bounds. But we'll come back to this a bit later. Now, okay, you probably heard about error bars in some other lectures, and you may wonder what is the difference between these error bars that people have shown in other lectures and the error bounds that I've shown in this lecture. Well, the error bounds, they are variance estimates. So they give you an idea of what is the variance of a certain quantity, your error, or the error that you make in estimating the parameter of a certain model. So, okay, let's assume that we have this variance estimate. We know the variance of the quantity that we are interested in. So how to use it? Well, we have this very nice equality here that is ready to use. That tells us that the deviation of random variable from its expectation is bounded by the variance divided by the size of the deviation squared. Okay, so same trick, inversion trick, we get a bound like this. Okay, fine. So now if we know the variance, we have obtained directly a bound from this. Why not? But you see that here, I mean, if you remember Stefan's lecture, there were this distinction between Champions League bounds and regional league bounds. And this is regional league. Why is that? It's because you here only require a condition on the variance of the random variable. So it may have, this random variable may have arbitrary behavior on higher moments, and you don't care here. But if you want to get the final result, then you should use the exponential moments. And if you use the exponential moments, for example, in Gaussian case, but that also occurs in empirical processes, you have something like this. So okay, the difference is quite mild. You replace this 1 over delta here, essentially by log 1 over delta here. Okay. Who cares? I mean, in practice, you usually don't even compute this quantity because that's a fixed quantity. It does not depend on anything. It's just confidence level that you use. But okay, so numerically, I mean, even if you were to compute this quantity, you would not really notice a big difference because the bounds are. I mean, that would not be the main factor anyway in your bound. But remember that, like what we had in the bounds this morning, we have something like log number of function plus log 1 over delta. So okay, maybe the log number of function might be bigger than log 1 over delta, so we don't really care. But it does matter on the other hand, because it tells us that here we know exactly the behavior. We know precisely what is the behavior of our random quantity. So we have a better control on how it behaves, and it means we have captured something. It may not be so obvious to you yet, but well, let's see. Okay, so that was coming back a bit to this thing here. The message is, if you know the variance of a certain quantity, that's good, but it's not as nice as if you know all the moments of that quantity, because then you can use exponential amount and you have a better idea of what's going on. Okay. But now there is another trick. So if you look at what people call error bars in Bayesian approaches, is the following. I mean, if you want to give it an interpretation in a frequentist sense. So the model is the following. You have, so let's say this is nature. Okay. And from nature comes some function, target function. The way this is generated is modeled as a probability distribution. So you have your prior here. Okay? And then, along with this comes a set of data. And this is instance distribution. Let's call it Px. And then what you do is you compute the value of this function on the data. Usually add some noise. And this is the data that you give to the algorithm. And what the error bars quantify is the variance that you obtain in the error made by your algorithm based on this data. As if it were, as if this whole procedure was repeated over and over again. So imagine you do this several times. So here you apply your algorithm and you get some error. Okay? And you do that many times. You go to nature, you ask, give me a function, gives you a function sampled according to this prior, some distribution of data, compute the values, add some noise, go through your algorithm, get an error. And you do that over and over. And if you look at the distribution of this guy, well then, something like this. And this is precisely the error bar. So the error bar quantifies the variance in the distribution of this error when this process is repeated. But, okay, the trick is, this never happens this way somehow. You cannot really, I mean, I don't know any real-world problem in which you can sample functions from a prior distribution. So mean, you cannot really give an interpretation to this unless this is really what happens. And in general, you're not able to sample functions from a prior because you are given a problem, say DNA microarray analysis, and what you can get is data from that problem, but not new problems from the same distribution. Okay, and even if you were able to do it, this is true, or the result tells you something about this distribution of this parameter here. Only if this is correct. If it's wrong, if you make the wrong assumption, then this maybe the error value is like this, but the true distribution is like this. You don't know. Okay. So what we do instead, I mean, the other approach, which is used in statistical learning theory, is to say, well, nature, if you want, but we don't even need it, but nature chooses a function, and okay, a probability distribution, and then what we do is we sample data. Actually, we don't even assume noise. I mean, the noise is coming directly with the data. And somehow we don't even care about the function. And this is the probability distribution on the pairs x and y. We have this data, run the algorithm, estimate the error of the algorithm, compute the error of the algorithm, and get some distribution. And what we repeat now is not this, but only this. Which means that the statement that we make in the end, they tell us that if we sample data over and over again from this distribution, which we can do basically when we have a database, we just take enough data, the error bound will hold with a certain probability, which means we have a characterization of the whole distribution. Okay. So that's what is meant here by error bound solved for both samples. We know actually what is the distribution of this error under the assumption that we are able to sample from the same distribution, no matter what happened before. So under this frequentist interpretation, which you may disagree with, for a given problem, if you look at a given data set, let's say, these error bars don't say anything. They do not characterize in any way the distribution of the error, because they characterize the distribution under something that you cannot sample. And even if you were able to sample, they just give you an idea of the variance, not on the full distribution. And they are correct only if the prior is correct. And there is no way to test this. So, okay, that's a theoretical point of view on this problem, but you can say, well, I'm an engineer, I want an algorithm that works, then, okay, fine, you can use them, but you should know what you're doing. Okay, now another thing related to bound. If you compute this bound that I showed this morning, you will be a bit surprised, I guess. Remember these Radmacher averages? So we have something like even empirical Radmacher averages. So we have the, okay, let's say the risk of G is less than the empirical risk of G plus some Radmacher average, let's say of the class G, plus something. Okay, so if we're doing classification, this is between 0 and 1, or between even 0 and 1/2, because our classifier is not completely stupid in general. Okay, so what we expect is that this bound gives us a nice idea of what this value is. But if you do it, then okay, this would be roughly 0 if you have a good algorithm. And this would be, I don't know, maybe 1000. So we say, okay, let's use that. I spent all my time doing complicated mathematics, but in the end I have some very trivial statements. Something which is between 0 and 1.5 is less than 1,000. Fine. Okay, so sorry for wasting your time. Okay, so now there are many people that say, well, how can we make this bound non-trivial in the sense that how can we get this right-hand side of the bound to be not that big and get something meaningful, non-trivial? Well, it's not easy. And actually, that's not the point. We don't care. That's my strong claim with the box. And okay, now I tell you why you did not waste your time. And there are three reasons. Well, there is one reason which comes at the end. And if you think about it, there are three levels in which you can try to use these bounds that I've displayed here. There is the quantitative level, which is this one. I compute the value and I try to see whether it gives me anything interesting. Another level is to do model selection, to use the bound to choose some parameters of the algorithm. And then the last one is the qualitative usage of this bound. And we'll see what this means. Okay, first level. Let's try to make use of these values. Well, as I said, in general it doesn't tell you anything. So you cannot, I mean, if you're an engineer, you're working in a company, your boss tells you, okay, you have this algorithm, nice, but I want to know what is your risk. You say, oh, wait, boss, I have a very nice, I have read a very nice paper by some theoretician, and it tells us how to compute this from the data only. Very nice. Okay, tell me what is the value? 1,000. Okay, you're fired. So, but there is a reason for that. And it's not that mathematicians are stupid or anything. It's just that it's a complicated problem. And well, here are some reasons. The behavior of these quantities, these errors, are quite complex, and they depend in a very intricate way on the algorithm that you're using. And in general, it's not easy to analyze these algorithms, especially when they are designed by non-theoreticians. Okay, anyway, so the techniques that are used to obtain these bounds, they are usually sharp, but only in the asymptotic regime. So if you take number of samples go to infinity, after some time, your bound will be less than 1. And then you have a nice value. But okay, so the techniques are really not appropriate in some way for finite sample or for small sample sizes. But anyway, that's not really a problem. I mean, there is this technique that would give you more precise or smaller values here, but you would not gain much because you would have to compute something which is very complicated, and it would become unreadable. And what we care about is not really much the value, but what it tells us about what's happening. Okay, so we need some kind of readability of the bound, and for readability we need to simplify things as much as possible. And in this simplification, then we lose lots of constant factors and so on, logarithm factors. But that's not what matters. So if you want to use them quantitatively, that's the answer. It's hopeless. Forget the bounds. Use cross validation. Okay, so what else can I do with the bounds? So that's the second level. So get a picture. So let's see. We have an algorithm that depends on some parameter. That's sigma. That's a trendy parameter. And we plot the error of our classifier obtained using this parameter. So it'll maybe look like this. And this is, this is. Now if we plot the bound, as I told you before, it will be, well, it won't be here, it will be much higher, but let's say it might be here. Okay, so if you have something like this, then it's already very interesting. Even though the value is much higher, you still have at least similar shape. You may not have the right minimum, the minimum of your bound may not be exactly at the same place as the minimum of the true error, but at least once you get this, you can say that you have achieved something. Because the bound really captures how the error depends on the parameter. So somehow, if you want to do model selection, and if you have a bound that has value 1000, you don't care as long as it has some kind of behavior like this. But yeah, again, you can say, well, but if I have a small bound, then it's more likely to be of the same shape, especially if it's a bound. But well, I never saw an example where a small bound was better behaved just because it was smaller. In general, small bounds do not take into account the same quantities as large bounds do, and large bounds, because they take into account these quantities, have the right behavior. But still, I guess the theory has not come to a point where we can have very precise estimation of the right value of the parameter. But okay, not too bad. So there is some hope, not much, but okay, if you can use cross validation. So then we go to the third level, the qualitative level, and that's the idea. What is the bound meant for? Is exactly this. We want to understand something from a mathematical analysis, and from the understanding that we gain on the algorithm, we want to improve that algorithm or to get a new algorithm. So even if we don't have the right parameter, it's okay still if we still have a rough idea of where it should be. So at least this bound, what it tells us is that don't take this parameter value or don't take this parameter value. And look for some parameter in this region. And that may be enough to get a nice algorithm, especially if you can make it computationally efficient. And somehow this bound, what it buys you, it gives you some robustness with respect to the choice of the parameter. But you should try to avoid some danger here, which are a posterior justification. So, well, we see what this means. And that's much more reasonable. So an example. If we look at how margin of a hyperplane, so we have some data. We look at possible hyperplane that separate this data. I did not have time to plot a picture here, but if you look at several hyperplanes that have different margins, then you might see that large margin is correlated to low error of the hyperplane. Okay, so then fine. The algorithm is let's maximize the margin, and hopefully we'll get a hyperplane which has low error. That's okay. We can do that. But the other approach is risky. Because let's say now we start with a bound that says large margin means low VC dimension. Then we should maximize the margin. That's risky. Even though that's almost what I told you here to do, there is something that you should avoid. And here is the catch. Okay, let's take a class of functions f, and we define some functional on f, omega of f, that gives us just non-negative number for each function in the class. For example, the norm of that function. Now if we take two real numbers x less than y, the set of functions that have the value of the functional less than x is obviously included in these sets where this level is higher. Okay, so we have set like this. So let's see, this is f. This is omega of f. And we are looking at these sets. So obviously they are nested in the sense that if we increase this level, we increase the size of the set. So assume now we are able to compute, or assume we want to compute the VC dimension or any, I mean I'm using VC dimension as a generic term here, any capacity measure of these sets. Then of course it will be increasing because we have a bigger set every time. So the capacity increases as a function of x. So if you look at this, you may say, well, okay, we have an algorithm. We want to minimize the capacity of our class of function, right? So let's minimize this function, omega of f. But that's, okay, where is the problem with doing that? The problem is that you can choose any function or any function of omega. Basically any function of omega corresponds to putting a prior on your class, and there is no reason to choose one prior instead of one other prior. So choosing, if you choose some quantity, omega of f, and you notice that the capacity is related to this quantity, it's not a surprise. It cannot be otherwise. I mean, the surprise is that, for example, there are non-trivial relationships. That would be a surprise. For example, if you have a class of function such that VC dimension is infinite for any set of this form, but some scale-sensitive dimension is finite, or some other capacity measure is finite and depends in a certain way on x, then that can be a surprise. But there is a lot of arbitrariness here, and somehow you should always, when you see a bound, you should always ask whether what you obtain in the bound comes from some prior that you have set on your class of function, choosing functions that are large margin, for example, or whether it's really something new that occurs, something that you did not expect in the beginning. Okay, so this is the final answer to this question. What is a good bound? Forget about the value, but try to capture some meaningful behavior. And do not put quantities in your bounds directly by choosing some sort of prior, because if you end up with this prior in the bound, that would not be a surprise. And try to find what is responsible for the fluctuation of your quantity and how it influences this quantity. Okay, so now, last part of the talk. What is the best approach? Okay, I just chosen 3 methods to deriving algorithm, and I mean, of course, many of you may ask, well, I have seen all these methods, which one should I choose? Next week, my advisor will ask me to solve this problem, and he will say, well, now you should know a lot about machine learning. You have been to this great summer school. So now you solve this problem. And, well, okay, what should I choose? Well, okay, again, red box. There are slight differences, but overall, they are doing more or less the same thing. When I say kernel instance here, I refer to kernel-based algorithm like SLT or other variants. And what they are doing is nothing but finding a trade-off between fits of the data and complexity. And they are just different ways of measuring this. So there are different ways of measuring the fit of the data. You have different loss functions, or different ways of measuring the complexity of the functions, function classes. And here, that's where you can put a lot of prior information. And, so it's basically up to you to choose these methods. And I would say don't expect that one is much better than another in terms of performance, but it's more in terms of usability and fits with your problem. But you can as well, but maybe you have some nice bound to show us on this method, and that would show that, I don't know, this is much better than this. Well, not really. I mean, if you look at kernel methods, for example, okay, you can get some sort of justification of large margin from the theoretical point of view, even though there is some risk here in doing this, as I told you before. I mean, one thing that comes out of the theory, which is definitely a good thing, and it's true, is that these kind of methods are not sensitive to dimension in a certain sense. But there is no justification for kernels or for using kernels or for choosing a specific kernel versus another kernel. So this is not, I mean, this is separate issues somehow. Well, Gaussian processes, there is not really much a theory. I mean, you can get error bars and all this stuff, and if you go back to the beginning of my talk, you see that it's not really a theory in the way that we think of it. But we could imagine to analyze this algorithm in the same framework, and we would not get much. I mean, we would not get anything new. We would, because in the end, at the end of the day, we minimize fit plus complexity, so we would have bounds that tell us what is the capacity of the set of functions and so on. And okay, same thing for NDL. I mean, more or less, you have a direct bound that comes out of NDL approach, which is that when you minimize description length, you get a set of possible choices that is limited. So you just have a bound that depends on the number of possible choices, which is, or the log of the number of possible choices, which is basically the length of description. And somehow you have more or less an easy bound that follows, but it doesn't mean much anyway. So, okay, so what is the right answer to that question? What is the best approach? Does not depend on who was the best lecturer to introduce you to these approaches. Does not depend on theoretical answer or theoretical bounds, but it depends on, I would say, and well, I forgot the red box, but so think of it. Think that there is a red box here. Depends on the nature of your prior knowledge and how your problem is stated somehow. So, let's say if you have a nice similarity measure that is natural in your problem, then try kernels. And if it happens that the similarity measure is a positive definite kernel, then you're in good shape and you can try this kernel method. Or if you have a nice coding scheme that comes to your mind immediately when you see your problem, then why not NDL? And if you have some sort of intuition about what should be the covariance of the outputs between two inputs, then use Gaussian processes. So it's up to you and up to the problem that you have at hand. So I come to my last slide. So what is learning theory for? I mean, what is the goal of learning theory? One partial answer is this bound. So if they are correctly used, then it's fine. You can get some understanding on what's going on. But this is more or less one aspect of the problem. And what would be nice is as Olivier mentioned yesterday, would be to be able to formalize other learning settings that go beyond classification or regression or supervised learning in a way. So maybe transduction, maybe unsupervised learning or semi-supervised learning, and try to see what are the relevant quantities in all these aspects, or I mean, all these settings. And what is needed above all is to provide practitioners or people that apply these algorithms new ways to ensure their prior knowledge or flexible ways of putting in your algorithm some knowledge. And I would say that, well, so far, the probabilistic approach, Bayesian approach, or whatever you want to call it, is very flexible, and there is no other approach that matches this flexibility in terms of modeling power. And so I will finish by these words of Vladimir, and thank you for your attention.